Okay, class, here's a summary of the way vectors work. If we have a vector that starts at P1 and ends at P2, we can create the position vector that starts at the origin with this simple formula. It's an equal vector because it's got the same direction and magnitude. We can add vectors by adding their component parts or subtract them. We can calculate the magnitude as the square root of a squared plus b squared. We can create a unit vector that shares the direction of v by taking the vector v and dividing by its magnitude, or we can solve this for v and we would see that the vector v is the vector v's magnitude times the unit vector. And we can also, this is very useful here, we'll be using this in a second here. So alpha is the direction angle between v and I. So we're going to take the magnitude and multiply it by the location on the unit circle for that angle, and this gives us some power to solve some problems, which we'll see here in just a sec. Okay, class, here's a summary of some of the theorems and useful definitions that we're going to tap into here. So if I've got a vector in space and it starts at point P1, ends at point P2, and then I can create the position vector, which is an equal vector that starts at the origin just by taking x2 minus x1 and y2 minus y1. Position vectors are easy to work with, so that's what we'll do. And then if I take those values, I can reference that now as a1, b1, or I can write it as a1 times the unit in the direction of the x-axis and the unit in the direction of the y-axis. That's I and j. Okay, and then here we add vectors by adding their component parts, subtract vectors by subtracting their component parts. We can scale multiply by multiplying each component by that scale. And we've just remember that we've got multiple ways to represent the vector. The vector's important idea here is the magnitude, and we can calculate any vector's magnitude by taking the sum of the square of the component parts and taking its square root. And over here we've got a way to calculate a unit vector which has a magnitude of 1, but we make it in the same direction as some vector v. And so this is creating a unit vector in the direction of vector v. We can solve for v, and we can see that the vector itself is just the magnitude times the vector component parts, and this represents the unit vector u in the direction of v. So this is a very useful formula 8 here that we'll use in the next example. Okay, so in this example here, we're going to find speed and direction of an aircraft. Now, velocity is indicated by both the magnitude and the direction, and the magnitude of velocity is called speed. Okay, so if we're doing a 500 mile per hour due south, then that's on the y-axis, so we're going to take that j component, and since our start point is the origin, we're going directly south, so that we're just going to take negative 500 times the unit j in the y direction. And then we also need the vector for the jet stream. It's 80 miles per hour in the northeasterly direction. So in this case, we're going to have to northeasterly, if we take it equal parts, that would give us a 45-degree angle here. So we have to create these vectors, and then we're going to find out this vector here, v sub g. So, okay, so for part A, we've got to come up with this v sub a. We've already got it in our picture here, but this is without any external influence. I'm going to be equal to negative 500, that's my miles per hour, and the negative gives us the direction. Okay, and so that's v sub a. The impact of the wind we're going to call v sub w. Okay, and this is where we have to think of it. There is an angle between I and v sub w, right? So we know it's 45 degrees. So this is where we're going to tap into that formula. And we're going to say, well, this one is equal to the 80 miles per hour. And to put it in a northwest direction, northeast direction, we're going to use a 45-degree angle, so our alpha angle is going to be 45 degrees. So we're going to say 80 is the velocity, and then in the direction vector for v sub w, and then the velocity is on the outside. So this is the unit, what I'm putting in here would represent the unit vector in the direction of v sub w. So that's going to be a cosine of 45 degrees, the I direction, plus a sine 45 degrees in the y direction of the j. Okay, so we've got the two vectors built. Okay, so let's keep going with this. So VW, this is the wind vector here. Cosine of 45 degrees is the square root of 2 over 2 times I. And the sine of 45 degrees, also the square root of 2 over 2 times j. Go ahead and distribute this wind jet stream here, and we'll get 40 times the square root of 2 I plus 40 times the square root of 2j. Or we can just go ahead and factor that out. 40 square root of 2, and then here we would have I plus j. Okay, so now let's look at what they're asking us next here. We want to find the velocity relative to the ground. We've got two different velocities influencing this jet. One is its own power, 500 miles per hour to the south, and then it's the velocity of the wind pushing it in a northeasterly direction, equal parts. So it's going to change things here from our desired result. It's going to push us off a little bit here, and it's going to create what they're calling the velocity relative to the ground. So combining these is just an application where we add the two influencing vectors together to get their combined result. So for part B, all right, I placed our results for A over here because we know that for part B, what they need is the sum of these two. We need the velocity relative to the ground equal to the velocity in the air of the plane plus the impact of the winds. Okay, so that's going to be our negative 500 j plus 40 square root of 2 I plus j. Okay, so if I just put these parts together, there's no I component in the aircraft speed. So we're just going to combine the negative 500 with the 40 times the square root of 2 as our coefficient to j. And then the only thing influencing the x direction is the 40 square root of 2. So I'm going to put 40 square root of 2 times I, and then a 40 square root of 2 minus a 500 are influencing the j. So here we're going to get 40 square root of 2 minus 500 worth of j. Okay, so let's remember that our magnitude, in this case, it's velocity, and it's given to us by the square root of the component parts of the vector. So I'm going to take the coefficient of I squared plus the coefficient of j squared. So for part C, I've rewritten the result for B down here. So this is the AI and this is the BJ. So I have to take, for VG here, it's equal to a square root of this component part, 40 square root of 2 squared. And then we have 40 square root of 2 minus 500. And we're going to square that. All right, to find the velocity relative to the ground, we need to put this into the calculator. So I'm going to just take the outer square root, and I'm going to enter parentheses to create this 40 times the square root of 2, another square root 2. I got an arrow right to get out of that radical in that, and then just hit this square it. We're adding another open parenthesis, 40 square root of 2 minus 500. Alright, so that should give us the answer. Okay, so 447 miles per hour, even though the jet is moving relative to the airspeed 500 miles per hour. But combining that with the resistant force of the wind, we've got a ground speed of 47. Okay, so far for C, we've found the speed or the magnitude from the component parts. Now we want to find the direction. We'll also get that from the component parts, because remember that this right here is how far we go in the x direction, how many units we go x, and then the multiple or the coefficient of j is how many units, positive or negative, we go j. And that's really where this point ends, right? Because this unit is now in standard position, so the end point is this coefficient by this coefficient. So because we know that the end point where VG ends is 40 times the square root of 2 for x, 40 times the square root of 2 minus 500 for y, we can use the inverse tangent to find what we're after. And remember, the inverse tangent is defined between here and here, so we are in the space where it's defined, so we shouldn't have to do any translation. If it were over here, we might have to translate, or over here. All right, so what we do know about the angle that creates the direction is that the tangent of that angle is equal to y over x, so it's going to be 40 times the square root of 2 minus 500 over 40 times the square root of 2. Okay, so theta is going to be equal to the inverse tangent of that. Okay, so we're going to enter that into our calculator. We're going to find the inverse tangent. So second tan, and then I have to open parentheses for the numerator and the denominator. So this will be open parentheses 40 times the square root of 2. Get out of the square root, subtract the 500, close the numerator parentheses, divide, open the denominator parentheses, 40 square root of 2. Okay, otherwise it would only divide by the 40 if I didn't group these together. And then got that. And I also have to close the inverse tangent function. All right, so we're looking at negative 82.73 degrees. Okay, so our angle roughly negative 82.73 degrees. Now you might see that written differently, like in your book they do show this as S7.3, and I'm going to say 7.3 I'm going to say 7.27. Right, because that makes up the difference between negative 90 degrees, right? So my perspective is from due south, so that's what that says. If I'm heading due south, I'm going an angle off due south of 7.27 degrees in the east direction. So I'm 7.27 degrees favoring the east direction from due south. So that's this measurement right here. And this is our plane. Okay, that's one application. Next application we're going to look at are force vectors. Okay, so these were velocity vectors.